Welcome to the answer video of the problem about the pipeline system. In this exercise, we want to pump wastewater from a mining process from one vessel to another. To start off, it's important to make a sketch in order to visualize the problem. First, the water is located in vessel 1. From here, it is pumped to vessel B through a pipe. The pump used has a capacity that we will call phi subscript W. We place point 1 and 2 at the surfaces of the liquids inside vessels A and B. The height difference between point 1 and 2, delta H, is 3 meters. We note the volumetric flow rate through the pipe, phi subscript V, which is constant. The pipe has a length L of 15 meters and a diameter D of 10 centimeters. The pipe has two 90-degree bends. In order to find the average velocity of the water inside the pipeline, we need to divide the volumetric flow rate, which is given, by the area of the cross-section of the pipe, which can be calculated with the diameter using the formula of the area of a circle. This gives an average velocity of 2.55 meters per second. Next, we are asked to calculate the required pump capacity, which we can find using a mechanical energy balance. It's a steady state, so the left side of the equality sign will be 0. So we start off by writing down a general form of the mechanical energy balance. We have the pressure term, the velocity term, the potential energy term, then the pump capacity, and the term of the energy lost due to friction. At point 1 and 2, the water is not moving, so V1 and V2 will both be 0. Z1 minus Z2 is the same thing as delta H, just the negative. And both vessels are open and thus in direct contact with the atmosphere, so P1 and P2 will both be the same as the atmospheric pressure, and the difference between P1 and P2 will obviously be 0. So if we consider these three things and isolate the pump capacity, we find phi subscript W equals the mass flow rate times the energy dissipation plus gravity times the height difference. Now we need to find values for these parameters, especially for the energy dissipation term. The mass flow rate can easily be found by multiplying the volumetric flow rate with the density of water. We find 20 kilograms per second. The expression for the energy dissipation term due to friction is 4F times the length of the tube divided by the diameter times half the square of the average velocity plus half the square of the velocity times the sum of all loss coefficients. So the ones of the dissipation at the entrance, at the exit, and at the bends of the pipe. So first of all, we need to calculate the Reynolds number in order to determine 4F. We find 255,000 and we fill this in the equation given for 4F, which is 0.4 times the Reynolds number to the power of minus 1/4. This gives 0.018. For the loss coefficients, we add together the loss coefficient at the entrance, at the exit, and 2 times the loss coefficient for a 90 degrees bend. You can find these values in the data companion. The result is 4.0. So what we do now, we go back to the equation we found for the pump capacity and we fill in all the numbers that we just found. and we end up finding 1024.3 watts. For the next part of the exercise, we need to find the temperature change due to friction. We set up a thermal energy balance, which is a steady state. So 0 equals the mass flow rate times the difference in internal energy of the water between point 1 and 2, plus the mass flow rate times the energy dissipation. Here we divide by the mass flow rate and we isolate U2 minus U1. U2 minus U1 can be rewritten as the heat capacity of water times the temperature difference between point 2 and point 1. Note here that we are taking the negative of what is written in our energy balance. And the expression for the energy dissipation due to friction is the same as before, and can thus be calculated using values found previously. We calculate the energy dissipation due to friction and we find 21.8 joules per kilogram. Now, if we isolate T2 minus T1 and fill in the numbers, we find a temperature rise of 0.0053 Kelvin. We are asked how much of the pump capacity can be saved if we use a smooth pipe. What changes here is that for a smooth pipe, we use a different value for F, which for a Reynolds number between 4,000 and 100,000 by definition is 0.316 times the Reynolds number to the power of minus 1/4. Next, we calculate the difference in energy dissipation, so how much less energy we would lose. We note that the rest of the values stay the same, so the only thing that changes here is the value of 4F. And thus, filling in all the numbers, we find that we lose 1.95 joules less per kilogram due to friction. If we multiply this with the mass flow rates, we find that this accounts for 39 watts of the pump capacity. Thank you for watching the video and good luck with the rest of the exercises. See you next week.